Let's take a look at this example. First, we're supposed to check how many nodes we have. We have one node, which is my reference one. Okay, so this is 1, and I have 2, 3, 4. Okay, I have 4 nodes. 4 nodes minus reference 1 is going to give me 3. It means I'm going to have 3 equations because I have 3 nodes. V1, this is my V2, and this is my V3. Like always, we're supposed to find Y's. We're supposed to find the admittance of each branch connected to the node. Now, as we said before, if you have resistor connected in series with the current source, you simply do not convert this to the admittance, or you can call conductance. Okay, so we are going to concentrate only on those which are not in series with the current sources. So I mean, we have to find Y2, we have to find Y3, and we have to find Y4 and Y5. So let's start. We have Y2 equals 1 over R2, which is equal 1 divided by 3 coulombs is equal 333.33 microsiemens. Okay, so this is my Y2. I ignored Y1 because it's in series with the current source. We don't have to find the admittance of it. So next we're supposed to find Y3. Y3 is equal 1 over R3. So I have 1 divided by 2.2 coulombs. And this is equal 1 divided by 2.2 exponent 3, 454.54 microsiemens. Okay, so this is my Y3. Next, I'm supposed to find Y4. Y4 is equal 1 over R4, which is equal 1 divided by 4 coulombs. So this is 1 divided by 4 exponent 3 is equal 250 microsiemens. Okay, next I'm supposed to find Y5. Y5 is equal 1 over R5. This is equal 1 divided by 2.2 coulombs, and we found already that this is equal 454.54 microsiemens. Okay, so this is one part of my solution. Next, I'm supposed to find Y11, where Y11 is the sum of the admittances connected to node 1. Okay, so as we said, we're not going to consider this one. So we have just one admittance, Y2, connected to this node. That's why Y11 is equal Y2, and this is equal 333.33 microsiemens. Next, we're supposed to find Y12, which is equal Y21. Okay, so this is the admittance between node 1 and node 2. Okay, so the admittance between node 1 and 2 is equal to the admittance between node 2 and 1. It's the same one. That's why I said Y12 is equal Y21. And this is equal to Y2. And again, this is equal 333.33 microsiemens. Next, I'm supposed to find Y22. Y22 is equal Y2 plus Y3 plus Y4. Y2 is equal 333.33 microsiemens plus Y3 454.54 microsiemens plus Y4 250 microsiemens. Okay, so Y22 is equal 333.33 exponent 6 negative plus 454.54 exponent 6 negative plus 250 exponent 6 negative. This is equal 1.03 millisiemens. So 1.03 millisiemens. This is my Y22. Now, but please realize that we have 3 nodes. That's why we have to continue. We have to find Y13, which is equal to Y31. Okay, as you can see, we do not have any admittance between node 1 and 2. I mean the one which connects directly node 1 with node 3, okay, because we have between them node 2. So that's why we are going to say that this is equal 0 Siemens. We write 0 Siemens because there is no direct connection between node 1 and node 3. Next we're supposed to find, let me write this over here, Y23, which is equal Y32. Okay, so this is the admittance between these 2 nodes. Okay, so this is nothing else, just Y4, and Y4 is equal 250 microsiemens. Next we're supposed to find Y33. Okay, so this is the sum of the admittances, okay, sum of the admittances of the branches which are connected to the node 3. So I have Y4 plus Y5. So I have 250 microsiemens plus 454.54 microsiemens. This is equal 250 exponent 6 negative plus 454.54 exponent 6 negative equals 704.54 microsiemens. Okay, so we found Y33. Next we're supposed to find the sum of the currents going to node 1. Okay, so let's take a look what we have over here. We have I1 leaving node 1, that's why it's going to have negative sign. I3 is coming to the node 1, that's why it's going to have positive sign. And I2 is leaving node 1, that's why it's going to have also negative sign. That's why I'm going to write that the sum of the currents at node 1 is negative I1 negative I2 plus I3. So I have negative 6 milliamps minus 5 milliamps plus 8 milliamps. Everything is equal negative 3 milliamps. Next we're supposed to find the sum of the currents at node 2. Please notice that node 2 is not connected directly to any current source. That's why I'm going to say that the sum of the currents at the node 2 is equal 0 amps. Next, I'm supposed to find the sum of the currents at node 3. Okay, please notice that the current node 3 is going to receive two currents, I2 because this current is going to this node, and I4. So I'm going to say that this is equal I2 plus I4. This is equal 5 milliamps plus 7 milliamps. This is equal 12 milliamps. Okay, so now we are ready to write the formula, okay, general formula for the 3-node circuit. Okay, so I have, keep in mind, Y11, anytime you see Y11, Y22, Y33, these coefficients are going to be positive. Other combinations are going to be negative. So I have Y11 V1 minus Y12 V2 minus Y13 V3 is equal sum of the currents going to node 1 negative Y21 V1 plus Y22 V2 minus Y23 V3 is equal sum of the currents going to node 2. Okay, so I have negative Y31 V1 minus Y32 V2 plus Y33 V3 is equal sum of the currents going to node 3. Okay, so now we are ready to substitute Y's and the currents by the numbers. So we found that Y11 is equal 333.33 microsiemens V1 minus Y12 is also equal 333.33 microsiemens V2 minus Y13, which is equal 0 Siemens. So 0 Siemens, capital S, V3 is equal sum of the currents going to node 1, which is equal minus 3 milliamps over here. Next, I supposed to write negative Y21, and we found that Y21 is equal 333.33 microsiemens V1 plus Y22, which is equal 1.03 millisiemens V2 minus Y23, which is equal over here 250 microsiemens, and this is V3, and this is equal sum of the currents going to the node 2. Okay, so this is equal 0 amps. Okay, so next we have negative Y31. Y31 is equal 0 Siemens, and this is my V1, and Y32 is equal 250 microsiemens, so I have minus 250 microsiemens, and this is my V2, plus Y33, which is equal 704.54 microsiemens, and this is V3. Everything is equal. The sum of the currents going to the node 3, which is equal 12 milliamps. Okay, so next we're supposed to plug in these equations into the calculator. Okay, so I have, you can do this of course manually, but if you can do this on the calculator, it's okay also. So we have 333.33 exponent 6 negative, and I have negative 333.33 exponent 6 negative, and I have 0, and I have negative 3 exponent 3 negative. Now second row, I have 333.33 negative exponent 6 negative. Next one we have 1.03 exponent 3 negative, and I have negative 250 exponent 6 negative, and I have 0. Next I have third row, so I have 0, and I have 250 negative exponent 6 negative, and I have 704.54 exponent 6 negative, and I have 12 exponent 3 negative. This is equal negative 6.93, so this is my V1. V1 is equal negative 6.93 volts. V2 is equal 2.06 volts, and V3 is equal 17.76 volts. Next we're supposed to find voltage across resistor R4. So this is voltage across this resistor. So VR4 is equal V2 minus V3. If you are going to subtract these two voltages, you are going to find the voltage across this resistor. So we found that V2 is equal 2.06 volts minus V3, which is equal 17.76 volts. This is equal 2.06 minus 17.76. This is equal negative 15.7 volts. So this is negative 15.7 volts. Next, we're supposed to find the current which goes through resistor R2. If you want to find the current, you're supposed to write the formula. I R2 is the voltage across this resistor divided by the resistance. So voltage across this resistor is the difference of these two voltages. So I have V1 minus V2 over the resistance R2. So I have V1 we found is equal negative 6.93 volts minus V2, which is equal 2.06 volts, divided by R2, which is equal 3 kiloohms. Okay, so this is equal negative 6.93 volts minus 2.06 equals divided by 3 exponent 3. This is equal negative 2.99 milliamps. So this is negative 2.99 milliamps. Okay, so this is my current which goes through resistor R2. Next, I'm supposed to find the current which goes through resistor R5. Okay, so this is the current which will go through this resistor. Please notice that the voltage across the resistor R5 is equal to the voltage V3. That's why I'm going to write that IR5 is equal V3 over R5, where V3 we found is equal 17.76 volts over 2.2 kilohms. This is equal 17.76 divided by 2.2 exponent 3. This is equal 8.07 milliamps. 8.07 milliamps. Okay, so this is my IR5. Next, I'm supposed to find the power, PR1. PR1 is the power at this resistor. Okay, please notice that this resistor is in series with the current source, so the current which goes into this resistor is equal to the current of the current source. So we have 6 milliamps going through this resistor. That's why I'm going to use the formula I1 square times R1. So this is 6 milliamps raised to the second power times R1, 1 kilo. Okay, so this is equal 6 exponent 3 negative the second power times 1 exponent 3. This is equal 36 milliwatts. So this is 36 milliwatts. Okay. Next, if I want to find PR4, so if PR4 is equal, okay, voltage across resistor R4. Okay, so we found it. This is equal negative 15.7 volts, but let me write the formula first. So this is VR4, okay, to the second power over R4. Okay, so this is equal negative 15.7 volts raised to the second power divided by 2.2 kiloohms. This is equal, let's calculate it. So I have 15.7 negative raised to the second power divided by 2.2 exponent 3. This is equal 112.04 milliwatts. So this is 112.04 milliwatts. Okay, let me remind you that VR4 we found and it was calculated, and is equal negative 15.7 volts. So at this moment we can say that the problem is solved.